Okay then, well, I'm going to explain the calculations that we performed to arrive at the conclusion we did. Now, I'm going to begin by listing our known facts. We know that let me see here, gravity, we're going to use feet. Gravity is negative 32 feet per second squared. That's the acceleration of gravity, and that's the same as negative 9.8 meters per second squared. We know that the door to the wall is, let's see, so the door to the wall is going to be 8 meters, and we know that the wall itself is 10 meters high. Now then, we calculated that the 1 meter parallel to the ground, the gun can shoot a dart between 28 and 31 feet, and we decided to use 29.5 feet. So we're going to say when it's parallel to the ground, we separate these things, the dart can go 29.5 feet. Okay, now the first thing we need to do, oh, and one last thing, the door itself is 2 meters tall. Okay, so now the first thing that we need to do is figure out the muzzle velocity of the gun. And we are going to do this by taking these values here and calculating how long it takes the dart to fly these 29.5 feet. Let me see, did I get that right? No. Okay, never mind. What we're actually going to do, sorry I got that wrong, is we know that however long it takes to fly these 29.5 feet, it will be the same length of time it takes for to just drop the dart 1 meter, from 1 meter to the ground, because we know that as it flies this way to the ground, it takes the same amount of time as if one had just dropped it. So by finding this, we can, and we know this length, so then we can figure out the speed by putting the distance it travels, the 29.5 feet, over the time it takes, which I'll call that x for now. Okay, so first let's draw this. What are we trying to find? We are trying to find, so the dart is going to fall 1 meter. We're trying to find that. And we have these values up here to work with. So, if we go to our kinematic equations, we can use this one to solve this particular problem. Sorry if I block the board as I write this. I'm not used to filming myself writing on a whiteboard. Let's see. So velocity final squared is equal to the velocity of the initial squared plus 2 times the acceleration. And we're going to call, let's see, how did I do this? We are going to call this, we're going to call up the positive x direction and this the negative x direction. So now then, where was I? Okay, 2 times the acceleration of the x final minus x initial. Okay, so we have that. Now let's see what we have here. We can start plugging things in. So that we don't know the final velocity. This is going to be a two-part. There are going to be 2 parts to finding the time here, because we are missing the final velocity, and we are also missing the time. So before we can find the muzzle velocity, we have to find the final velocity here, and then the time it takes to fall this far. So this is part 1, and we're trying to find this final velocity. So we're going to begin that by saying, let's see, velocity final squared is equal to, let's see, is equal to the initial velocity, which is going to be 0, because we're dropping it from rest. and then that's going to be times. And actually for this I'm going to use meters because we'll convert it to feet later, but right now if we just work in meters, that'll be okay. And I like doing that because it's the metric system, which is all base 10, which is easier than saying 12 inches in a foot, etc. So plus, let's see, 2 times the acceleration, which is, for now we're going to say negative 9.8 meters a second squared. Times x final. It's going to be this is going to be 1 meter, I believe. Yes, because it's falling a distance of 1 meter. Minus x, which is going to be negative sign there, and which is going to be x initial will be 0. And we had to put this negative there because we declared that this up here is the positive x direction. So the ground, it is falling in the negative x direction. So by the end of its flight, its final position will be negative 1 meter, but it's in the negative direction. Okay, minus 0 because the initial position is meters. Initial position is 0 meters. So now then, we can solve this like so. Let's take that out. 2 times. Okay, oops. To remember to keep that. Oh, sorry. 2. Okay, now when you work that out, that'll give us, let's see, 19.6. Negative. Positive. Okay, now we're going to have positive because we have negative and negative. Meters squared over seconds squared. But we have to take the square root of that because we have the squared here. So our final velocity is going to be equal to 4.4 meters per second because the square root takes out this and this, but we know that we're falling in the negative direction, so we're going to go ahead and add back our negative sign there. Okay, I'm going to erase the board, keep this final number in mind. We're going to use this in the next part to calculate our time. Okay, now I'm going to start again. Now where we left off, I've erased the board, so we're going to start with a blank slate, as it were. Okay, so where we left off, we had figured out that the velocity final is equal to negative 4.4 meters per second. Now then, like I said, later on all of our measurements will be in feet, but for now just finding the time is easier to do this with meters. And now we know that so now we know the velocity final, we know that the velocity initial is equal to 0. Yes? Yes. Is equal to 0 meters per second because remember we're dropping it from rest. And we know that the acceleration, negative 9.8 meters per second squared. And so now, but we don't know the time. So, to find the time, we can use this kinematic equation. Velocity of the final is equal to the velocity of the initial plus the acceleration times time. And with this, we can say, just start plugging these in here, negative 4.4 meters per second is equal to velocity of the initial is 0, so we're not going to have one of those. We're just going to drop that. Then the acceleration, negative 9.8 meters per second squared. Time, which we don't know, obviously. So now then, let's divide this out. And when we divide out the negative signs, because we have 2 of them, they'll go away, they'll cancel. Then our meters and seconds will cancel out, but remember this is seconds squared, so on this side we're going to be left with just seconds, which is good because we're trying to find the time. And then once you divide that out, you're going to be left with the time is equal to 0.44 seconds. So, what is this answer that we've gotten exactly? It is basically this. We know that the object was 1 meter high, and that it takes 0.44 seconds for the dart to fall 1 meter. Now, because we also know that the time it takes to fall from rest like this is going to be the same as it takes to go this distance here, we can put this distance, which we calculated before, if you remember, as 29.5 feet. So now we can take this and put it over the time. And this is going to give us our muzzle velocity of the gun. And once you divide this out, you will get 67 feet per second. So now remember this. Now this is the muzzle velocity of the gun. Okay, welcome back. Now, we're going to take a break. Remember, we're going to use that muzzle velocity we found a second ago later on. But for now, we're just going to try to find the angle of the arrow as it is shot. So we're going to do that a couple of ways. The first way is we are going to take and find, we know that this wall, we're going to go back and use the measurements we had earlier. This wall here, say this is the wall, it is 10 meters high. And then we know it is 8 meters to the door. And so this is the door. This is 2 meters high. So what we need to find out is the angle that the arrow will enter the door, because we know that the arrow will fly like this. Which is a triangle, and this angle will be the same. So by finding the angle of entry, and say the bottom of the door's here and then the wall's here. So by finding this angle of entry, we will know this angle that we'll have to shoot it at. Okay, so let's begin. I'm going to erase this moment. Okay, now, so we have this. So it would be easy enough if we just use the tangent, negative tangent, because we're trying to find this angle here, and that will give us, so meters over 8 meters, and then the meters would cancel. And now this is going to give us, do this out, 51.3. 51.3 degrees. So, from the top of the wall to the bottom of the door is going to be 51.3 degrees. But, what if we don't want to get from to the very bottom of the door? What if we want it to go through the door, which that'll give us a better example. That'll decrease the likelihood of us missing entirely if we can get it to go squarely through the middle. So what we're going to do, we're going to redraw this here. I'm going to redraw this over here. New diagram. Okay. This time, because we know the wall is 10 meters high, and we're going to want to shoot like this. We want to find this angle now. So, because this is 2 meters high, we're going to subtract that from 10. We're going to get 8 meters. And then we know that this distance won't change, even though we've elevated it a little. So this will also be 8 meters. So now, if we do that, we automatically know that for these two to be both 8 meters, this must be a 45, 45, 90 degree triangle, which means that this angle here is going to be 45 degrees. And this further will allow us to know that we have a range now. We have 51, so we can go from 51.3 degrees to 45 degrees. Actually, I probably should have reversed those. So we know we need to fire the arrow somewhere between these two measurements. So let's add them together and divide by 2. And that'll give us 96.3, which divided by 2, that will give us 48.1. Approximately. Now, it should be noted that with all these variables, we have rounded throughout this equation, so the numbers that we get in the actual answer may vary slightly because of rounding. But this is what we have so far. So this degree, this is the degree that it needs to enter at to go squarely through there and land in the back of her cell. Also, we know that this is the degree at which we should shoot the arrow. Now this is the last step of the problem, and actually at this point when we were doing our experiment we stopped because now we knew the angle of elevation that we needed to shoot at, and so we stopped and we did some tests to figure out how far away we had to be to make the arrow go through the door. Now we are going to figure out mathematically how far away we need to be. Now I'm going to say in advance that the numbers we got mathematically did not match up to our experimental values, which means that there was either an error in the way we calculated it, which there could be, there might be, but I don't think that's the case, or else there's a conceptual error. We are missing a key piece of information, or we've overlooked something important. So the math is right. It's just there's something else, a key factor that we've missed, and that's causing our numbers to be wrong. And I'm more inclined to believe it's the latter rather than the former of our math being off, because that would not be good. Well, no, never mind. I'm going to edit that out. Okay, so what are we going to do here? Let's draw a diagram. This is essentially what we have here, the flight of the dart or the arrow. Now, we know that this is 48.1 degrees. And we need to figure out how far this is. And so to do this, and we know the muzzle velocity of the gun, which we calculated earlier at 67 degrees. Very well then. Now, not degrees, at 67 feet per second. So now what are we going to do? If we can find this distance from here to here, then we can use sine, cosine, and tangent to find out this distance. So let's begin with that. Okay, so let's call this the x initial and this the x final. So now we know that the x initial, we're going to be starting at 0 meters. And let's look at this rather than on a slant now. We're just trying to find this, using this information that I'm laying out now. We don't know what our x final is. We don't know how far that distance is, but we will. We know that the velocity of the initial, now that's going to be the muzzle velocity of the dart leaving the gun, is 67 feet per second. And we know that the final velocity is going to be 0 feet per second. Now, the reason we're able to say this, I know I drew this flat like here, but up here we can see that it's going to reach its highest peak, and at the very peak of its flight, its final velocity is going to be 0, and then it's going to start its downward slope. This is going to be a negative velocity, so from here to here is all positive velocity, and it's decreasing until it reaches 0 at the apex, and then it will increase in a negative direction. And the acceleration, we know that that is negative 32 feet per second squared. Okay, so now let's just begin this with a kinematic equation, because I am very fond of kinematic equations. Velocity of the final squared is equal to the velocity of the initial squared plus 2 times the acceleration times x final minus x initial. Now, okay, where were we? Okay, feet per second squared, so that's the acceleration. And this is going to be, again, multiplied by the x final, which is going to be, this is the part we don't know, minus the x initial we know is, we said was 0 meters. So we're just not going to worry about that. There. Now we can just start working out the problem like a normal math problem. We know that this will go away, and that this will become, once you multiply all that out, 4,489 over second squared plus 2 times the acceleration, so we're going to say negative 64 feet over second squared x final. So, moving on this theme, we can move this over here, but actually it'd be better if we didn't, if we moved this over here and said so now we have this. And now, well, this actually would become positive. And so once you reach this point, it is merely a matter of division. And we know that these feet cancel these feet. It'll cancel one of these feet, so we're just going to be left with feet. And then these 2 seconds, they'll cancel each other out. And we're going to see that x final is going to be equal to 70.1 feet. Now, what is that exactly? That, if you remember, is this distance here. So, and we know the angle that we're going to be shooting at. And now, using cosine, we are able to determine what this distance here is. And this is the distance that we wanted initially here. I'm gonna write up here now, just for sake of room. So we have the cosine of 48.1 is going to be equal to the x over, which is the adjacent, over the hypotenuse, and then it's just a matter of cross multiplying, and we're going to get, when we do this, we're going to get 46.8 feet. But that's only one of these lengths. we're going to have to multiply that by 2. And that should give us this total distance, which comes to be 93 feet. So, according to this math that I have just shown you, we should have to be 93 feet away from the door when we shoot the arrow. This is not the case, however, as we saw in our experiment, that while mathematically we said we should be this far away, in actuality we were only 30, approximately. All these are approximate numbers, but we were approximately only 32 feet away. This is how we did our calculations, though, and I believe now Jeffrey, if I'm not mistaken, will talk to you a little about our conclusions.